Hello, and welcome to week 2 of Ecology 4253. So we've gone over the basics of what is ecology and sort of introduced you to general ecological concepts in the first lecture. And now we're going to start at the level of the population and talk about population growth and decline. I think a lot of population and ecology textbooks in general start here because it's conceptually simple and then allows us to add in the complexity of individual level variation to go down to the individual level, but also allows us to scale up to the community level by considering multiple interacting species in what start to be simple models and then turn out to maybe not be that simple. So with that, I'm going to share my screen and we can dive into it. So suffice it to say, today we will be talking about population dynamics. The reading for this week is this right here. It's chapters 1 and 2 of a book by Nicholas Gotelli, The Primer in Ecology. It goes into far more detail than I will present. You pretty much only have to know what I present, but this resource is fantastic and I would expect you to read it. And so if there's like a test question that you're saying, I can't find it on the notes, it might be somewhere in that chapter. But really, like, the notes should cover everything that would be on a test. I think the Gotelli book is mainly for providing some more context. And so it's weighty. That reading is, I think, at least like 30 or 40 pages. But it contains a lot of like figures, but also a lot of really useful information to really clearly explain single species population dynamics. And specifically the two models that I think we'll largely focus on today, which are just sort of exponential growth and logistic growth, but we'll also talk about some matrix modeling approaches as well. And so without further ado, let's dive right in. I'm going to move that down there. All right. So questions about what controls the abundance, meaning the number of species in a population over time of a given species, is like a fundamental question in ecology. And you can't really get at it by simply doing field observations, right? Because like this species might go from having 1 individual to 10 individuals to 2 individuals to 5 individuals. And is that comparable, or how is that comparable to a different species that reproduces in a different way, right? So we have like asexual reproduction by budding, or you have sexual reproduction, which a lot of organisms have, but then have different numbers of individuals produced, right? So like if you have a clutch size, which is like the number of individuals per reproductive bout of like 20 versus 1 or 2 or 1, it sort of leads to very different dynamics. And so we need some way to operationalize or get at population dynamics in a very generalized way. And we can do that using simple models of population growth. And so the ones that we'll go over today, there are 2 specific like sort of submodels, but this sort of first part is a very generalized, almost like word model of what it means to have a population changing through time. And so here on the side of the equation, we have n, which is a notation for the population size of that species. So we have some number n of individuals in a population. And these are individuals at time t+1, meaning they're 1 time step in the future. And so this is saying what controls the number of individuals in a population in the next time step, tomorrow, next week, next generation. So that time scale can vary. And so we might think that the number of individuals in the population at time t would be quite informative, right? If there's 10 individuals in a population today, then chances are there's probably going to be somewhere around 10 tomorrow, right? So that's our base assumption. But then there are other processes that can go on, right? And so we have like an individual can die, an individual can be born. And so we have all of a sudden birth-death processes where you have birth here, as I'm highlighting in the notes, and death here. And so death affects population size negatively, birth affects population size positively. And we also have these two other terms that I include here, which is the idea of immigration and emigration. So immigration means the flow of individuals from neighboring environments or patches into this population that we're defining as N. Right? And meanwhile, emigration is individuals that are in patch of population N leaving and emigrating. So dispersing to other patches. However, we're going to even simplify this further. We will relax the strict assumption that we're about to make in later models, but not here. We're going to say this is a closed population. And what closed population means is, imagine you took like one of those things they put around cakes in like the diner, right? The big glass things, the dome things, and you just put that around the population. So there's nothing going in, nothing coming out. It's a closed system. Birth and death are the only two processes we need to really care about. And there could be tons of other processes acting, right? So there could be competition with other species or with your own species for resources. You could consider modeling the resource explicitly. Like what if you have a consumer resource interaction, as we'll go over sometime this semester, and a species depletes the resource at a given rate, right? And then you have to consider the ability of the resource to replenish in models of population dynamics, as the ability to consume resource is related to the ability to give birth, right? To produce more of one of yourself, of your own individuals of your population. And it also may be related to death in terms of extremes like starvation. All right. I remember when I first taught this, I drew a continuous model on the board. So in considering continuous time, and people's eyes just glazed over. So I will largely be talking about all of these models in terms of discrete time. And I alluded to that previously when I said at time t+1 and time t, but the units here matter, right? And so time t could be any time labeled t, but time t+1 means that the unit of t has to be such that it's meaningful. And so typically it would be considered to be a generation. And so you're sort of assuming non-overlapping generations, which means that individuals reproduce and then die. And then at time step t+1, that's like a new cohort of individuals, if that makes sense. This doesn't strictly have to be true, especially for individuals that give birth multiple times. If you can assume that the population growth rate is going to be the same. So individuals reproduce multiple times such that at time t they could reproduce and they could still be alive and would die with some probability or at some rate proportional to that. That's introducing a little more complexity than I think we're ready for. So let's just consider it a little bit more abstract. And we're just going to look at how these models would work. And to do that, I'm actually going to sort of make some quick and easy plots in a language called R, which will hopefully be helpful. This was also something that I tried to do with the last class that I taught, and they looked at me as if I had 3 heads. However, I think if I explain it clearly, it'll actually help solidify a lot of points around how these models work. And so let's consider a single species, a population of a single species growing at some rate. And this rate we're going to call the growth rate of the population, which we annotate using lambda. And so we have the population at time t+1, so just the same thing as above here, is equal to lambda the population growth rate times the population size at time t. What does this mean functionally? What this means functionally is that this is the population growth rate. If it's above 1, the population will grow. If it's below 1, the population will decline. If it's equal to 1, nothing happens. That means that at every time t, the population produces enough individuals to replace itself, but not to add any extra individuals, if that makes sense. So if this is equal to 1, that means that we can basically ignore it, such that it's like saying nt plus 1 is equal to nt. All right. I'm actually going to move this outside of the window so you don't have to see the script. And now what I'm going to do is run some code that I wrote to look at exponential growth. Okay, so I'm moving over here a plot. And this plot shows different values of lambda and the phase space, or the space between the population size at time t on the x-axis and the population size at time t plus 1 on the y-axis. And you see that there are 3 lines, with blue line corresponding to the highest population growth rate, and the green line corresponding to the lowest population growth rate, which is just below 1.75. So eventually that population will decline to extinction. This line is the red line here in the middle is the 1-to-1 line, meaning that population growth rate is equal to 1. The population will just replenish itself and not do anything else. But this is not super duper informative. It just sort of shows that growth rate matters in terms of the slope of this relationship. So if you have a higher growth rate and given some population size, so if we drew a vertical line right here, if we had 40 individuals at time t, then in the next time step, that shouldn't be, whatever. It will have less than that. And then, oh, it's 40. So maybe that intersects with something around, no, it's way higher. I don't know what's going on there. Basically, that green line should be such that it's below 40. That red line should be such that it is 40. And that blue line should be such that it's above 40. I think we can ignore that and move on though, because it's easier to conceptualize and see when you consider the time series dynamics. And so what I mean by that is not to just consider time t and t plus 1, but to consider time t plus 2, t plus 3. And so for that, okay. And so, oh, that's why, hold on. All right, let's just consider this first case. That'll be easier. So the case when you have a lambda value greater than 1, because there was something with how I coded it, but let's just say we have a lambda value, so we have a population growth rate greater than 1. How do we expect this to look as a function of time? If we start out with 100 individuals, how many individuals will we have at time t equals 10? So 10 generations or time steps, however you want to look at it. And what we see, and I guess what sort of this alludes to here, is that the population grows exponentially, which means it increases and then sort of has a, not a doubling effect, but a quickly compounding effect of population size, because it has no upper limit, right? We're treating lambda as if it's a constant value, and this will just increase until infinity. And so if we plot that out for 50 time steps, it'll look even more wild. And I can do that really quick. There it is. And so all of a sudden we see this y-axis changed. And is this reasonable? Like, is this a description of any population? Probably no, like not really, not at all. Although initially invading species, so a species that occupies or colonizes a new area, may experience something resembling this before something stops it. And so I think it's that something stopping it that is interesting. And so this is a very simple model. It's a very simple model, which is wrong. But it provides a good conceptual basis for developing further models. And so we would expect that something reduces population growth rate at some point, right? When you get up to being 6 times 10 to the 17th number of individuals in a population, you're going to run out of something. You're going to run out of space. You're going to run out of food. Those are the two main things that you'd be competing for, probably. And so here I go into a little bit about the continuous time model. I don't really want you to worry too much about this. We'll talk about it in class, but I'll sort of skim by it now. The one thing that I would like you to pay attention to is that now, so what this is saying is the change in the population size as a function of change in time. So dn dt. And so hopefully you brush up on your calculus and have an idea of what this is looking like. And it looks really similar, right? It looks really similar to the discrete time. But now we're saying time is continuous. So imagine cutting up those time slices into smaller and smaller and smaller pieces until, in the limiting case, the difference is tiny. Piece is tiny. The piece is almost non-existent, and it's continuous. So there's a difference here is that R is something different than lambda, right? And so lambda is actually, or R is actually the log of lambda. And so here, this is, because this on the left-hand side is the rate of change in n, in the population size as a function of time, such that if this quantity is greater than, if this quantity is greater than 0, the population will grow. If this quantity is less than 0, the population will not grow. If this value R. If this value R is equal to 0, then that means that the rate of change, dn dt, is equal to 0. And the population will remain at whatever the initial population size was. So I think here in this plot on the right, I started it with 20 individuals. Okay. And this becomes important in a second, because we have to think about what these models mean. What are they telling us? And what would the dynamics of the model be if we started the model under different initial conditions? And I'll get to that in a little bit. But before I do that, I'll talk briefly about how this can be used, how the continuous time version can be used to extrapolate and turn back into discrete time, basically. And so if you differentiate this equation, you can actually start to get at what the population at any time t would be, right? So instead of having to simulate it like we did here, where it's like, I need to know the population at time t minus 1 in order to get at the population size at time t. I need to know the population size at time t in order to estimate the population size at time t plus 1. But this is a very simple relationship such that I should be able to estimate the population size at time t only by knowing the initial conditions, meaning my population size at time 0, and then the population growth rate, which is little r. Little r is also called the instantaneous rate of increase. And so that's one way to start differentiate between population growth rate lambda, which is a per capita measure, and then instantaneous rate of increase, little r. Yeah, read the notes, think about that one. It's not super important, but distinguishing in your mind between little r and lambda, useful at least. And so this is a way to actually predict population size at any given t, given the initial population size, and then the little r, population growth rate, and then the value of t. So if you want time set 10, t equals 10. It's useful. But this sort of hints at something, and that's that initial population size really matters. So this gets us to thinking about ideas of population equilibria. So an equilibrium, as we'll talk about on Thursday, is a position or population size, so something, it's a number of individuals in a population that causes the dynamics to be stable or potentially unstable. I don't know if that was that good of a definition, but here we go. We're gonna think about it and like sort of define it by thinking about it further. Because initial conditions matter, like I said before. So if I start that population with 20 individuals and I simulate it forward, it follows an exponential curve. What happens if I start that population with 0 individuals? I know that's odd to think about, but in that case, you would just have 0 individuals in the next time step. And you would always have 0 individuals. And so anytime this rate of change, anytime we can make this rate of change equal to 0, we have found an equilibrium, meaning that through time, the value will stay the same. This can happen in the case of extinction. So like when I said, what if we had 0 individuals in a population? That's extinction. You're going to have 0 individuals moving forward, barring any immigration from a neighboring patch. But we can also see equilibrium points that aren't so arbitrary. Here we won't, right? In this simple model, there's no upper level, right? If I start at 10 individuals, I'm just going to go to infinity. So I guess in a sense, infinity is an equilibrium, but that's not really an equilibrium. And so here we'll go into, oops, sorry. Oh yeah. So this is the bottom part. I don't want to spoil it or have you guys read ahead. I'm just kidding. Okay, if you read ahead. So it's good to think about and know the analytical relationship between little r and lambda and how the continuous model is related to the discrete model. And then also these, and so I said these aloud, but I'll sort of say them again so that we can get on the same page, because these two models are the same model, right? In continuous time or discrete time, it is drawing the same exact curve. And so the relationship is that when you have a lambda that is less than 1 or an r, a little r less than 0, you have population decline until 0. So you'll see a population crash. If you have lambda equal to 1 or a little r equal to 0, you have no change in the population. It's a flat line. It's incredibly uncommon. This doesn't happen. Or if you have a lambda greater than 1 or an r, a little r greater than 1, you'll have a population increase to infinity. It'll just keep on going. And so now I want to introduce the concept of stability of equilibria. So we said, we acknowledge that this model has one equilibrium point. It is 0. If I start the population with 0 individuals, I know that at the next time step, there will be 0 individuals in this model, given the assumptions. But this can take on 2 different forms. An equilibrium can be unstable or it can be stable. Unstable means, an unstable equilibrium means if I start at 0 individuals and I perturb the system a little bit away from 0 individuals, let's say like I add 2 individuals into the population, does that go back? Do I rebound and go back to 0 individuals? Or do the dynamics change greatly, right? So we can imagine a situation. Let's just give the exponential model for an example. We start with 0 individuals. We have a population growth rate, a lambda greater than 1, or little r greater than 0. I introduce 2 individuals to that stable, or sorry, not stable, that equilibrium of 0 individuals. The population subsequently takes off and grows exponentially. That equilibrium was unstable because when I perturbed the system, the dynamics ran away from that equilibrium point. What would happen if I had little r less than 0 or lambda less than 1? I add 2 individuals into my population that is initially size 0, that equilibrium point. The dynamics are such that that population will eventually, in finite time, go back to 0. So if I perturb the system away, I give the system a little push, it'll go back to the equilibrium. That is a stable equilibrium. It sounds relatively simple. It'll get slightly less simple as we go and talk about other models and we talk about cycles and cool stuff like that. So get excited for that, but hopefully that makes sense. And if not, I'll go over this on Thursday and clarify points. And so this model is super duper, like we don't expect to see any of this in natural systems, not even like bacteria, right? That are given like all the resources they can use. You're still gonna see some initial cap. You're still, or some eventual cap where resources run out or space runs out or there's competition. There's no competition in this model. And so this model makes a ton of assumptions. First being that it's a closed system. There's no immigration or emigration. Secondly, there's a constant little r or lambda, however you want to view it, doesn't change over time. Also, individuals don't differentially contribute to population reproduction, right? So there's no age structure, as we'll talk about later, or size structure or genetic structure. And so this can happen when you have variation as a function of one of these things or something else that causes individuals to not be equivalent in their ability to reproduce. A very simple example of this would be sex ratio or sex structure in the population. And so if you have 90% males and 10% females in a population, you're fundamentally limiting your growth rate, your potential growth rate, relative to if you had a more equitable sex ratio, given a sexually reproducing species. So yeah, these are things that we'll try to address the complexity of later on, but for this, at this point, we just need to acknowledge these as assumptions that we're making. And so now I want to talk about logistic growth because it's super cool for a lot of reasons. The first and foremost of it is that it introduces a little bit of realism into the model. And so here we have exponential growth where things just go to infinity, but we know that there's like an upper limit, right? A population, an area can only like have so many individuals packed in there before it like levels off, right? And so this is sort of what is attempted to get at using the logistic model. And so let's go through it and I think you'll see how this works. And so we have discrete model down here. And so we're still trying to explain the population size at time t+1. And it's still a function of the population size at t, but now it's in addition to the population growth rate lambda multiplied by the population size at time t modified by this thing, right? Okay, and so what this thing is 1 minus the population size at time t divided by this notion of a carrying capacity, which we say is k. A carrying capacity is the maximum population size that the population is expected to get. There's only so much space. There's only so much resource. There's something limiting the bounds, and this is the bound. The bound is k. So when k is equal to nt, this quantity, I'm trying to highlight it, this quantity total is equal to 0. So no matter what lambda is, no matter what nt is, this entire quantity will equal 0 when nt is equal to k, meaning population size at time t+1 will equal the population size at time t. All right, I think that makes sense. I think I also have a sort of plot of it. Let's see what we got. Yeah, don't even worry about that one. That one's a little bit confusing. I think I got, oops, sorry. Do I want to? I don't want to talk about that. I can. Maybe on Thursday we'll go into this. This is a very nuanced plot that I feel like is not strictly necessary when introducing the logistic equation, but maybe for talking about some of the nuances as we will discuss them in class. But I think here's what we care about is the dynamics of the system. Why did I set the X or the Y limit so high? All right. That's really loud. I apologize for that. I get too many emails, some would say. All right, so we're going to look at this over 20 time steps. And this is what happens. I'm moving this back over. Okay. Start with a population of 30 individuals. We follow them over 20 time steps, and this is the situation where lambda is equal to 1. So nothing's changing. Carrying capacity is also 30. So the population is at carrying capacity. Let's now consider a case where we have any number of individuals at the initial population size, so N0 is somehow it's referred to, varying between 5 and 30. But the carrying capacity is still 30. This is what we get. And so here, our initial population size, if we follow each line, consider each line as a population. So this line starts with 5 individuals. It increases quickly and then saturates and fixes at 30. It hits its carrying capacity and stops. So I'm moving a little box around. I don't know if you can see that. I hope it's not distracting. In this case, the blue line is now this starts at 30 individuals. It stays at 30 individuals. All right. Okay, and we can use this to think about equilibria, stability, and what things would look like depending on population growth rate, right? So we can imagine a situation where little r is 0. That's what that would look like. Meaning, so I start the population size below the carrying capacity 30, but since r is equal to 0, the population doesn't change. It just remains the same at whatever starting point. This is also not something that's realistic. We're never going to see this happen. But it's interesting to think about because it starts getting us to the point where we can think about the actual behavior of the model. And so let's now consider a positive r, an r of 1.5. Actually, before we do that, you know what? Let's just go ahead and define stability and think about what happens with our different parameters, right? Because we have 2 main parameters we can tweak or alter. We have our initial population size, which we can't tweak, we can consider. And then we have our population growth rate, either the intrinsic rate of increase little r or the per capita growth rate lambda. And so we can look at our behavior. It's the same as the exponential model to a sense, to an extent, but not, it's got that k now. And so the k is that carrying capacity, where we naturally assume that they have to be greater than 0, because otherwise it doesn't make any sense if they are not. Not necessarily little r. Little r can be less than 0. And if little r is less than 0, what we see is that the population will decrease to 0. So the same as the exponential model. So that behavior is the same. This behavior is also the same. If you have a lambda of 1 or a little r of 0, the population does not change, as we see here. We have x as time, y as population size. We're tracking a population, not changing it through The difference is here, where we have lambda is greater than 1 or little r is greater than 1. The population doesn't increase to infinity. It now increases to the carrying capacity k. Sweet. Easy peasy. This model also has a bunch of assumptions. It assumes everything the previous model did. In addition, it assumes constant carrying capacity. And so this k value doesn't change as a function of time. And also assumes a linear form of density dependence. And so population size can limit population growth, and each individual does so equally. How this would sort of not play out is you can imagine a situation where juveniles or smaller individuals might take up less space or use less resources. Here, an individual is an individual is an individual and contributes equally to the carrying capacity, or to the model, to getting toward that carrying capacity, which then influences the dynamics of the model. All right, and so here's where the fun starts of the logistic map. And so let's think about the equilibria of this. If we start with 0 individuals, that is an equilibrium right here. And so we have a population size of 0, and we have a little r that is something non-zero, right? Because if little r is less than 0 and population is 0, that is a stable equilibrium. Because if I perturb that system, it's going to go back to 0 because the population growth rate isn't high enough to support the population. So it's just going to go back to 0, stable equilibrium. If it's greater than 0 or greater than 1, if it's lambda, then that equilibrium is unstable, right? Because then I add and it starts and it grows sort of quasi-exponentially. It grows a bunch and then it saturates at k and then it continues going for a while. But we also have a new equilibrium, and that's k. K is our carrying capacity. And so let's plot it out where r is equal to 1.5. And that's kind of neat, right? Okay, so what are we seeing here? We're seeing that if we start with, let's say, 5 individuals, by time step 4, it looks like, I've hit the carrying capacity, but I've slightly gone over it. And so now I'm above my carrying capacity. When I'm above my carrying capacity in the logistic equation, that means that my n of t, I'll go to this model, my n at time t is greater than k, which means this quantity is negative, which means my population size is going to be my population size at time t minus some quantity, meaning I'm going to lose individuals. And that's what happens. It bounces down, overshoots again, bounces back up, overshoots again, bounces back down, overshoots ever so slightly, and then hits carrying capacity. This phenomenon here are called damped oscillations, right? And so we're not just sticking at k and staying there, but k is still an equilibrium point. So having an n equal to k is a stable equilibrium if r is greater than 0. If little r is less than 0, it is an unstable equilibrium point. Yeah, I was thinking because if you push it up and you like add individuals, then wouldn't it stay up there for a little bit? But now, like, it will just like plummet past k and then go to 0 because you just don't have enough of a high enough feeding of individuals into the population to keep your population at k. It was dropped to 0. But this doesn't really explain the weird behavior we're already seeing. And so this is what happens when you have damped oscillations. This is when little r is equal to, this is when lambda is equal to 1.5. Yeah. So I'm making sure it's not little r. In the code, I wrote it as little r because I'm a fool. Okay. I don't know what time I'm at. I think I'm going to stop at this point, at this break point, and then we'll talk about structured populations I'll either add to this video if this is short enough, or I'll discuss it in class on Thursday. And so now we're talking about the logistic map. And so here we have damped oscillations when little r is, or when lambda is greater than 1.5. Let's consider the case where we ramp it up to 2. All right, so this is what happens when you start a population at carrying capacity and then have an R. Let's add a horizontal line in there at the carrying capacity so you can see. All right. So now the oscillations aren't damped. They're persistent oscillations, right? This is like called a 2 cycle. So it's going from some population size below the carrying capacity to above it, to below it, to above it, and not ever damping down to stay at carrying capacity, which means that K is an equilibrium point, but the actual time that the population is, if you go out and measure it in the field and say, I'm going to count the number of individuals, I know K, so I should be able to count K number of individuals if they're at equilibrium. You will never count K individuals, unless you consider these weird little intersections that are like in between time points. What happens when we start ramping this up? So let's say like we have the population growth rate. All of a sudden we mash up to like 3.2. Then it gets messy, right? The carrying capacity of this population is still 30 individuals. We never see it stay at 30 individuals. What we see it at is, I'm going to reduce the number of steps so you can see some of the dynamics. All right, maybe a little bit longer. What we see is that it bounces back and forth way above 30 or way below 30 in a sort of like period doubling way. And so you see it goes up kind of big, low kind of big, up not that big, low kind of not that big, up much bigger, down way almost to 0, where you're like, oh, that population is almost extinct, and then sort of repeats that sort of motif that it started. And I think what's sort of interesting about this model is that it's a simple deterministic model that you can extract these you can extract these interesting behaviors out of. And so you can have this situation where you have some species that should stop at K, but all of a sudden we have these cool oscillatory dynamics out of a simple deterministic model. And then what happens when you push that population growth rate past 3.5 or 3.6 or so is you approach. Okay, so that's the population. So that's the carrying capacity. Oh, I didn't make the number of steps long enough. I'm sorry. Let's increase that to like 50 should be enough. Maybe not. That's almost still looks like it's reasonable, right? It still is crazy. It's like, sorry, it's still all over the map. It still hits 0 at some times, which means that population is extinct. But it's not as extreme as it can get. So you still see some sort of order to it. But so I'm increasing just by a little bit more the growth rate. And what you'll start to see is that it approaches what is known as sort of deterministic chaos, where we're not able to estimate the population size at time t by knowing the initial population size and the carrying capacity. It starts approaching, deterministic chaos, which we can talk more about if people are interested. It's hard because normally I'd be looking at like students and being like, is this track? Are you getting this? But can't really do that. It's pandemic. So that's sort of interesting. And what I want you to get out of that is there's 2 population models. There's a concept of the stable and unstable equilibrium, which is really important. And this simple model that only has, I guess, 2 parameters, little r and k, can actually have some really complex behavior, which I think is really interesting. The last thing I introduced in this chapter, which is better if I can draw it on the board, is the idea of an Lee effect. And I think, so an Lee effect is, it arises from situations when you have birth or death processes that depend on the population size or density. Density meaning the number of individuals within some given area. So how this happens is, like, let's say if population size, I actually think I have oh yeah, I do have this open. Oh man, I have this freaking thing ready to go. All right, so let's consider this like some demographic rate on the y-axis. So that can be, I'm drawing lines. I don't know why I'm drawing, how I fix that. All right, so we have maybe birth, that's a B for birth, or maybe death, it's a D for death. Is birth easier to think about? Yeah, let's go with birth. So we have birth rate as a function of, why am I writing out population size? You guys know the notation now, right? As a function of the population size at time t. This would typically be, okay, I'm gonna switch colors. I'm gonna put the expectation in red, where you have, or sorry, the expectation in black, where you have a birth rate that is independent of, oh man, that was bad. Let's go switch it to the line. All right, that means that the rate that individuals are born doesn't depend on population size. Okay, that makes sense. This only makes sense in the logistic model, right? Because at some point there's gonna be a carrying capacity K. And so let's put it in right here. Can I change the color after the fact? No, of course not. So let's say there's a carrying capacity here, and we will label that K. And now it's time for me to butcher this because I don't know how to draw curves effectively, and my freehand's going to be really bad. I'll draw it in blue. So what this will look like in the logistic model is something, probably something like that, where there's some population size where birth effectively goes down to 0 potentially. Okay, I'm not going to get into details of this. An Lee effect happens when you actually go beneath 0, like that. All right. And so in this parameter space, in this little bit right here, it means that there's some positive number of individuals here, whatever that number n is. Okay. So there's some number of individuals n right here that's non-zero, because this is assumed to be 0, which causes birth rate to be 0 or like at 0 and then go negative. How this can happen is if, in many ways. One way is called a mate finding Lee effect. And so if sexual species can't find mates, then it fundamentally ties birth rate to the ability to find a mate, which may be contingent. It's probably contingent on the number of individuals in the population size, because if there's more individuals, then you have a higher shot at finding. There we go. You have a higher shot at finding a mate and therefore increasing birth rate. And so this is essentially the Lee effect. Hopefully the sort of conceptual way I explained it. Oh God. Sorry. Hopefully the conceptual way I explained it makes sense. And hopefully this plot also makes sense. Okay. And with that, I think I'm going to leave the bit about populations for the next lecture. But basically, now is when we start incorporating variation in things like age structure or stage structure. So we start considering structured populations. Nice. So thank you very much, and I hope you're doing great. Stay safe, and I'll see you next time.